Hello everyone, this is Indrani of Institute of Aeronautical Engineering College. Today I want to continue the analog and digital converters. The topic is under the subject name of the IC applications, as well as it will come under the linear and digital IC applications or linear and digital integrated circuits. Okay, so basically last time we have seen that this is the basic functional diagram of the analog to digital converter. So the analog to digital converter in the short form we will represent as a ADC. So what is the basic diagram of the ADC? Here ADC is nothing but analog to digital converter. We are giving the analog input signal and the circuit is generating equivalent digital output. A binary output can be generated. So here, if you see the definition here, it is a converter which will convert the analog signal into the equivalent binary, n-bit binary coded digital output. So here, the basic system diagram we are showing here is ADC. For that one, we are giving the input is the analog input and there is a reference voltage is given for the conversion of the analog signal into the digital form. With respect to the reference voltage, it will convert the analog signal into the equivalent binary form it will convert, right? So here, as I told you, here for this ADC, start, that is nothing but start of conversion, and EOC is nothing but end of conversion. So before we are giving the analog input signal for the ADC, first we need to press on start off button. Later we need to apply the analog input signal as well as the reference signal. Then later there is a conversion of the analog signal into equivalent binary form will be done. Later, after completion of the entire process, automatically your ADC will switch on the end of conversion. Okay, so this is the process that will be done. So here basically in the last class we have seen what is the classification of the ADC. What is the class here? Yeah. So basically the D equal to B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus and so on Bn into 2 power minus n, right? So out of this, see the B1 is nothing but the MSB bit and Bn is the LSB bit value, right? So here basically ADC is classified into two types, direct type ADC and integrating type of ADC, right? So if you remind the direct type of ADC, what is the direct type of ADC? In this direct type of ADC, here there is a further classification of the direct type ADC into 4 groups. So basically direct type ADC, it will compare the analog signal with the internally generated equivalent signal, right? So here whatever the reference signal and everything is there. So here whatever the external analog input signal is there, the external analog input signal is compared with the internally generated signal that will act as a reference signal for the corresponding circuit. So under this direct type of ADC, we have seen the flash type converter, counter type converter, servo tracking converter and successive approximation type of converter, right? So these are the 4 type of data converters we have seen. Out of all the converters, which is the best one? The successive approximation ADC is the best one we can tell here. Okay. So whatever the conversion time it is taking, the conversion time it is taking is very less amount of time it is taking here, right? Compared to remaining all the cases, right? Suppose if I want to convert 8-bit for the analog input signal, there is a equivalent, I will get 8-bit means the successive approximation resistor will take only the 8 clock cycles. 8 clock cycles of time it will take. Suppose if I go for counter type of ADC or servo tracking type of ADC, for the n bit conversion for the analog to n bit conversion, it will take 2 power n minus 1 time cycles of clock cycles it will take. But coming for the successive approximation ADC, for the n bit conversion, simply it will take the n clock cycles, right? N clock cycles it will take here. It is very fast. The other types of the ADC is the integrating type of ADC. What is the integrating type of ADC? Here, in the integrating type of ADC, here data conversion, analog to digital data conversion will be done in the indirect manner. If you see the previous name, in the previous one, this is the direct type ADC. In the direct type ADC, whatever the analog signal is there, the analog signal always compared the corresponding analog input signal with the internally generated signal. Based on the comparison, it has generated the equivalent digital output. Digital output has been generated. But coming for the integrating type of ADC, in this integrating type of ADC, the other name of this one is indirect type of ADC. Indirect type of ADC means here, first we will give the analog input signal. Whatever the analog input signal is there, the analog input signal is converted into a signal which is a linear function of time or frequency. Then we can get the equivalent digital code word based on the time and the corresponding frequency. We will get the equivalent digital code word by the counter type of circuit. Okay, so if you observe here, there is no any internally generation of the reference signal. Here in the indirect type of ADC, whatever the analog input signal is there, the analog input signal is converted into the signal which is a linear function of time or frequency. Later, whatever the linear function of time or frequency is there, that will be converted into equivalent digital form by the counter type of arrangement. Okay, counter type of arrangement. So under this, today we are going to see what are the indirect integrating type of ADC. In the last class, we have seen the direct type of ADC. So if anyone having the doubt with respect to direct type of ADC, please go through the lectures. Then you can listen what is the direct type of ADC and its classification and operation. And coming for the integrating type of ADC, this integrating type of ADC is further classified into two types. So the one is the charge balancing ADC and another one is the dual slope ADC, right? Charge balancing ADC and dual slope ADC. Both are the integrating type of ADCs or indirect type of ADCs itself. So in this charge balancing type of ADC, something it is making the charge, right? Something it is making the charge. What is the charge it is making here is, let us see. The principle of charge balancing ADC is, first it will convert the input signal into the equivalent frequency form by using the voltage to frequency converter, right? So as I told you in the definition, the input analog signal is converted into the linear function of time or frequency. Here, under the charge balancing type of ADC, we are converting the input analog signal into the equivalent frequency form by using the voltage to frequency converter. Later, whatever the frequency is there, the frequency is measured by the counter type of circuit and it is converted into equivalent output code. Whatever this equivalent output code is there, who has converted that? Whatever the counter is there, counter has measured the corresponding frequency. After measuring the corresponding frequency, it has converted the frequency into equivalent digital code word. Whatever the output code word we are getting here, the output code word is proportional to the analog input signal. Next, here the mainly what is the advantage of this charge balancing type of ADC? Here for this charge balancing type of ADC, simply there is a no further extra circuit is there for this. Simply what will happen, you can estimate. So here we are having the basically a voltage to frequency converter will be there, right? So what are the voltage to frequency converter is there? The output of the voltage to frequency converter I am giving as the input for the counter, right? So here for this voltage to frequency converter, I am giving the analog input signal. The analog input signal is given for voltage to frequency converter like this. What is the main advantage of this converter? Suppose if there is a noisy type of signal is also present. Okay, so here whatever the noisy type of signal is present here, the noisy type of signal is also converted into equivalent frequency form. Okay, we can get, even though I will get the exact counter type of output I will get here. Whatever the noisy signal is there, the noisy signal is, assume that the noisy signal is generally in the order of microvolt or nanovolt. Whatever the analog input signal is there, the analog input signal is in the order of volts or millivolts. Whatever the volts and millivolts is there, along with that, if there is a noisy type of signal is adding, simply it is a very less value. Even if it is a very less value means the corresponding counter doesn't count the corresponding noisy. What are the small changes there? It will ignore the corresponding change. Due to that, even the noisy type of signal is present also, I will get the exact output, digital output I will get here, right? So that's why the advantage of this converter is, even in the noisy type of environment also, I will get the exact equivalent digital output I will get for this type of circuit, right? So next, what is the disadvantage of this? The main limitation of this one is here, mainly the circuit output, it depends on what is the voltage to frequency converter. So the complete performance depends on the voltage to frequency converter. Voltage to frequency converter means we will use the type of components here is the resistance and the capacitance components we will use. So whatever the resistance and the capacitance components are there, they will deteriorate with the time being, and the corresponding both the resistance and the capacitance values depends on the temperature parameter. So obviously, if the room temperature increases, or if you are using the components for a long duration of the time, at the time the voltage to frequency converter cannot work properly, and at that time I will get a wrong output I will get here. This is the main limitation with respect to this charge balancing type of ADC. Okay, so next, so to avoid this situation, to overcome this drawback of this charge balancing type of ADC, we are going for the next type of ADC is the dual slope ADC. Dual slope ADC, right? So dual slope ADC. So here the name itself it is telling dual slope ADC. 2 times we are getting the slope curve. We are getting the slope curve for 2 times we are getting here. So let us see because of what and what 2 times we are getting the corresponding slope curve for this one. So here if you see here in this dual type of ADC, there will be some integrator type of arrangement will be there. The integrator circuit. The integrator circuit will generate ramp type of signal. Suppose if I take the integrator, for the integrator, how will be the circuit diagram of integrator? This is the right. So this is the integrator circuit. So for this integrator circuit, if I give the type of input signal is the analog input of sinusoidal signal, if I am giving, at that time it will generate the ramp type of signal will be generated. Yeah, ramp type of signal will be generated. And at the same time, if the input signal is a positive, if the input signal is positive, I will get the output value V0 is a negative ramp will be generated. That is for the positive cycle of the input like this. I will get the negative ramp signal like this I will get here. Why I am getting? If you remind the basic expression for the integrator, if the input of the integrator is Vi, then the output voltage V0 equal to minus 1 by RC into integral of Vi into dt. So from this, I can write this one as minus 1 by RC into del into Vi into delta t. If I represent some time period 0 to t or something else, if I represent here, this is the basic function, basic equation for the integrator. So minus 1 by RC into Vi into del of t, right? So means if I give the positive signal as the input for the integrator, I will get the negative type of ramp type of signal I will get. If I give the negative type of input for the integrator, I will get the positive type of ramp I will get here, right? So this is a small introduction about the this integrator circuit, right? So now coming back for here. So here in the dual slope type of ADC, basically we are having one integrator circuit is there, and the integrator circuit is generating the two ramp signals it is generating. How it is generating the two ramp signal? One is due to the unknown analog input voltage Vi, and another ramp signal will be generated due to the negative reference voltage, right? So here one of the input is I am giving is a unknown analog input. Whatever the analog input I want to convert into the equivalent digital form, I will give one time I will give that one as the input, right? Whatever the analog signal you need to convert into digital form, that signal I will give as a input for the dual slope ADC. Another time what I will give is for the same integrated circuit, another time I will give the input for the integrated circuit is there is a reference voltage signal. That is a reference voltage signal I am giving is the negative reference voltage signal I am giving here. So one time I am giving the positive, one time I am giving the negative. As I told you, if I give the input signal is the analog input signal which is having the positive analog signal, at that time I will get the output is a negative ramp. A negative ramp will be generated, right? So suppose if the input itself is a negative, at that time I will get the positive ramp at the output. So two times like this some slope type of waveforms I will get for this. So hence because of these two types of generation of the ramp signals, we are calling this one as a dual slope A to D converters. Dual slope A to D converter. So basically the name came from the how many number of slope curves I am getting, how many number of ramp signals I am getting. One is the positive ramp signal and another one is the negative ramp signal is generating. So due to that we are calling this one as a dual slope ADC. So this is the basic diagram of the dual slope ADC. First observe what is the thing that's going on. So here we are taking one switch type of arrangement here. So the switch one time can be connected to analog input, another time it will be connected to the reference voltage it will be connected, right? So next based on the type of input, whether it is an analog input or reference voltage input, that concerned input is going as an input for the, what is the name of this circuit? Just identify. What is this circuit? Here the name is given as a ramp generator. What is that ramp generator? This is nothing but your integrator circuit. So here this circuit is a integrator. So whatever the analog input or reference signal is there, I am giving as an input for the integrator, and the integrator output is given for negative terminal of the comparator circuit, and the positive terminal is given to ground. What is the function of the comparator? according to the function of the comparator. So here, for the comparator circuit, if one terminal is short circuited to ground and another terminal I am giving is a Vs is the another input. When here, what is the purpose of this comparator? Just it will compare the voltages at the positive terminal and the negative terminal, right? So here, when the positive voltage is more than the negative voltage, I will get the output of the comparator becomes logic 1, right? So when the negative voltage become more than the positive terminal voltage, I will get the output of the comparator equal to logic 0, I will get here, right? So if you observe here, whatever the positive terminal is there, the positive terminal is simply short circuited to ground. So whenever the positive potential become more than the negative potential, I will get the output of this comparator value equal to 1. Otherwise, we will get the output of this comparator equal to 0. So here, the output of this comparator is given as the input for the gate circuit, right? So for this gate circuit, what is the other input I am giving for the gate circuit? Here, the clock signal is the another input signal I have given for the gate circuit. So here, the clock signal continuously it will generate the clock pulses like this, right? Continuously it will generate the clock pulses. This is the clock pulses that can be generated by the clock, right? So now, if you observe, when you can get the passes of the clock signals towards the output of the gate, when the Vg value equal to 1, at that time, the AND gate will allow the clock signals through this, right? Suppose if the output of the comparator equal to 0, at that time, does not allow any passage of the signals. Does not allow any passage of the signals. So next, here what are the clock signals are there? The clock signals has been given as the input for the 4-digit decade counter. So 4-digit decade counter means here simply it will do the counting operation, right? So from 0 to 9 numbers it will do the counting operation. Yeah. So later 4-digit decade counter has been given, and here for this one I have given the counter detector for time T1 has been given, and whatever the output of this decade counter is there, 4-bit decade counter, that has been given as the input for the 7-segment decoder. This 7-segment decoder will display the output on the LEDs, right? So if you see the main circuit here, this is the control circuit. So who is controlling this switch type of operation and this conversion process and everything is this will be under the control of the control circuit. So from this control circuit, there is a reset type of pin is there, and there is a strobe type of arrangement is also there, right? So now let us see what is the operation that is going on now, right? So here first initially the control circuit will reset the corresponding decade counter. When the control circuit resets the decade counter, initially the decade counter will set all the logic values counted by the values. What the counter is just to simply do the counting type of operation. So it will reset the previously stored value and all the bits values are kept to 0, right? So later, once the reset operation is over, the control circuit will automatically connect the switch to the analog input voltage of Vi. When the analog input voltage Vi is given, we don't know what is the analog input voltage value, right? So definitely I will get the analog input voltage value is a positive analog input voltage value I will get here, right? So when the analog input voltage value is positive, now this analog input voltage I am giving as the input for the integrator circuit. So if the Vi value is a positive, I will get output of the integrator is nothing but a negative type of ramp signal I will get like this. Negative type of ramp signal I will get, right? So here after that, when the negative type of ramp signal is coming from here to here, when the negative type of ramp signal is coming, at that time, what is the output of this comparator? when the negative ramp signal is started, at the time the output of this comparator equal to logic 1, because here the ramp signal is nothing but a negative ramp. When the negative ramp is coming as the output of the integrator, at the time the comparator positive terminal voltage is more compared to the negative terminal voltage. When the positive terminal voltage is more compared to negative terminal voltage, at the time the output of this comparator is equal to logic 1, right? Output of the comparator equal to logic 1. When logic 1 is present, at that time your gate will allow the passes of the clocks and your decade counter will count the clock cycles. The decade counter will count the clock cycles. So, in the counting of clock cycles, whatever the counter is doing the counting operation here, and at the same time, while doing the counting, whatever the values are there, the values will be counted with the counter detector timing T1 also. So here, how many number of clock cycles that can be allowed by the gate here is, here whatever the analog input signal is there, the analog input signal is converted into equivalent ramp type of signal, negative ramp signal for a period of 2 power n into t clock cycles. 2 power n into t clock cycles. Up to that duration of the time, your counter, it will take the time to convert the analog signal into the negative ramp type of signal. So this time period T1 is nothing but 2 power n into capital T. Okay, 2 power n into capital T. So here whatever this time is there, this time is nothing but it is the conversion time. This is the conversion time to convert analog input signal into equivalent negative ramp signal, right? Negative ramp signal. Once this time period T1 came to 2 power n times of T, automatically your control circuit will change the switch position from this analog input to the reference voltage signal here. So here this time your reference voltage, your switch can be automatically connected to the reference voltage of minus V reference, and at the same time once it is setting the switch position from Vi to minus V reference, at the same time it will reset the corresponding counting operation, because previously your counter has counted for a time period of 2 power n into t clock cycles. It has counted the number of clock cycles that has been allowed by the gate circuit is 2 power n into t clock cycles. During this time period, the input analog signal is converted into the negative type of ramp signal, right? So later, once control circuit has resetted, whatever the 2 power n into t counting value is there, that will be reset and again it will come to 0, and at the same time your switch position will change from analog input voltage to the reference voltage position minus VR position. Immediately the switch position gets changes. Now for this switch, negative reference voltage is given, and indirectly this one will going as a input for the integrator circuit, right? So for this integrated circuit, previously where your integrator circuit is standard, because here previously I got the negative type of ramp signal for the analog input signal I got, right? Negative type of ramp signal I got as the output of the integrator circuit. Just assume that the potential value at that time is Vs is the potential value. So that's why it is represented as a Vs like this. Yeah. So previously for the positive analog input, negative minus Vs came as the output. So here towards the negative slope side, my Vs is present like this. Now I have changed the corresponding switch position from positive to negative. When I am changing the position from positive to negative, generally if I give the negative input for the integrator circuit, what is the output it will generate? It will generate the positive ramp output it will generate. For the negative type of input it will generate positive ramp output will be generated. But if you consider the previous case, previously where your integrator is present, the output of the integrator is stuck at minus Vs. Now this ramp has to go from negative ramp to the positive ramp like this, right? From negative ramp to positive ramp, when the reference voltage value is given as a minus Vr is the reference voltage value, at that time your ramp signal will be changes from the negative type of slope towards the positive type of slope, right? So during this time, when the conversion process is going on, during this conversion process, what is the input of the comparator? The input of the comparator negative terminal is simply a negative voltage minus Vs itself, because here it will come to 0. Otherwise, for all these values, I am getting the negative Vs only, negative voltage only can be present as the output of the integrator. Now again, your positive potential became more than the negative potential. At that time, the output of this comparator equal to logic 1. Now this time, your clock pulses will be passed through this one. So exactly what it will do is, your counter will count how much amount of time that can be taken by the circuit to bring back the previous negative slope to grounding. Okay, how much amount of time that can be taken by the circuit, how much amount of time that can be taken by the circuit to bring the previous integrated value from the negative slope towards the 0th value like this. So whatever the time duration it is taking here, the time duration it is taking to bring back this signal to the original value, whatever the positive ramp it is going on, positive slope it is going on, the duration can be counted by the counter. So here, once the counting is done, that counting is nothing but it is indirectly the equivalent digital value for the previous analog input signal, right? So how much time it is taking here? The time is there. The number of clock cycles it will take is some n. What are the n signifies is there? N is nothing but n number of bits. N number of the bits. So this n signifies the equivalent analog input, the digital value for the equivalent analog input signal. Okay. So previously what happened? Your counter has counted when I am giving the analog input signal for this. It has counted the whatever may be the slope value. It has done the corresponding signal is going towards the negative ramp side for a duration of 2 power n into t clock periods. Continuously 2 power n into t clock periods will be goes. But if the switch position has changed from the analog input voltage to the reference voltage, obviously, then what will happen is this time it will count how much amount of time to taken by the circuit to bring back the slope value from this minus Vs to 0th potential. Okay, 0th amplitude. So what are the duration is there? The duration is represented as a n number of clock cycles. That n signifies the equivalent digital value for the analog input signal. Equivalent digital value for the analog input signal. So whatever that n is there, that will be displayed. That will be given as the input for the 7-segment decoder, and this one will give what is the equivalent binary value. What is the equivalent binary value? So like this, we are getting the two slope type of curves we are getting for the dual slope type of ADC, right? Now, let us see the output waveform of the integrated circuit in form of the dual slope, and let us bring one relation in terms of the time period. Okay. So this is the plot between the time versus the voltage plot, and this plot is for the integrator output plot. Okay, this is the integrator, because here the integrator is a main component, the integrator output part. So here initially whatever the analog input signal Vi you have given here. During this part of the time, it has been integrated the corresponding analog input signal, and once the corresponding clock period is nothing but 2 power n into t cycles of clock periods till 2 power n into t clock cycles. It will do the integration of analog input signal, right? So after that, when the switch position changes from the analog input voltage to the reference voltage position VR, the negative voltage position VR, then at that time your integrator is taking this much amount of duration of the time. This duration of the time it will take is the n number of the cycles, right? This time period is fixed. Here the slope is fixed slope, means here we will get the slope in the reverse form, like this it will get here. Now at this point of time, what will happen? Here when the negative reference signal is touched towards the zero, immediately if you see, when the negative reference voltage touched the zeroth potential, then this is 0 and this is 0. Both are equal to 0, 0. Then at the time, the output of the comparator circuit equal to logic 0. When the output of the comparator equal to logic 0, at the time, your gate does not allow the passes of the signals. When there is a stopping of the signals, then your counter also won't get the clock cycles, and then it can understand that the conversion of analog to the equivalent digital form is over. Then whatever the final value, up to how much time it has taken to do this conversion process, the time duration n cycles is nothing but the equivalent binary output values. Okay, that will be displayed by the corresponding 7-segment decoder, and finally for the display here. Now, so here, what are the time it is taking for this conversion process? This T1 time, the T1 is given by minus Vs equal to Vi by Rc into T1. So why minus I have taken? Suppose if I find what is the integrator output, if I am giving the input of the integrator is Vi, what is the output of the integrator? Vs equal to minus 1 by Rc into integral of Vi into dt. Right? Integral of Vi into dt. Now, if I do the integration here, what is the value I will get here? Now, whatever this negative is there, I kept this side. At the time, 1 by Rc into Vi into capital T1. So, that's why we got this value. Okay, initially I have given the input voltage value equal to Va and the integrated output value equal to, at this time, till time T1 here, the integrated output value equal to minus Vs. Minus Vs equal to Vi by Rc into time T1. Right? Similarly, we need to find how much time it is taken to bring back the corresponding slope value from the negative to 0th potential. So here, the conversion cycle to bring the corresponding positive ramp, cycles to bring the positive ramp. How you got the positive ramp? Because of the negative reference voltage. Already your reference voltage itself negative. So for the integrator circuit, I have given this time the negative reference voltage is applied as the input. At that time, the output of the integrator equal to minus 1 by Rc into integral of minus Vr into dt. At that time, if I see, this is the final expression of Vs. Vs equal to minus Vr by Rc into T2. So, in the previous case and the present case, both are the Vs terms itself. Right? Both are the Vs terms. Now, I can equate both the equations. Yeah, previous case time T1 and present case time T2, both are Vs. So, I can equate both the time periods. So, this is I can equate here. If I equate these two terms, then Rc gets cancelled, and remaining term you will get is minus Vi into equal to Vr into T2 by T1. This T1 value is fixed. What is the T1 value? 2 power n into clock cycles of T. Right? So, here this is the reference voltage value. this reference voltage value is also fixed reference voltage value. Now whatever the time T2 is there, the time T2 depends on the input analog input voltage value. If analog input voltage value it is increasing, the time period also increases. If the analog input voltage value is less, then the time period also less. Means the equivalent binary value becomes a less value. Okay, so I think it's understand up to here. Now let us see what are the advantages and disadvantages. So here the dual slope ADC it is a more accurate. This is a integrating type of ADC. In the direct type already we have discussed 4 types. So this dual slope ADC will come under the integrating type of ADC. Before that, charge balancing type of ADC and dual slope ADC both will come under the integrating type of ADCs. What is the advantage of this one? The advantage of this one is this is a more accurate among all ADCs types, and it is a greater noise immunity is there compared to other types of ADCs. What is the drawback? What is the drawback here is it is a very slow process. What is a slow process? What is a slow process is it is taking 2 power n into t clock cycles for the integration of the analog input signal, and at the same time again to bring back the negative ramp towards the zero, towards the positive ramp side. At the time it is taking the number of cycles it is taking is n number of cycles. So total time period what's happening? 2 power n into t plus n number of cycles it is taking, and at the same time long amount of time it is taking. So that's why this is the slowest ADC. Next, it will achieve the better accuracy and it require high precision of the external components. Suppose if the external components are not working properly, because in the integrator we are taking the resistors and the capacitors. Suppose if the op amps is not working properly, at the time we can get the accuracy will be gets reduced. Somewhat erroneous values we can get. The equivalent analog can be converted to digital form with a error value, right? So these are the drawbacks with respect to dual slope type of ADC. Now with this concept, the total ADC classification, direct type, and in this session we have seen the indirect type. In this indirect type, the charge balancing type of ADC, and that is dual slope type of ADC. About these things we have discussed. So till now your analog to digital converter portion is over, right? So I think it's clear. If you have any doubts, please ask me in the next coming session, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.